Dear students, good morning. In this session, we shall discuss greatest integer functions. Followed by this, we'll have a couple more problems based on this topic. So here do we go. So before we move into the greatest integer function, we shall recollect a couple of basic definitions which we have discussed earlier. The first definition is divisor and second definition is division algorithm. So B divides A if and only if A equal to B into C, where C is some integer. So this is the basic definition of a divisor. So I can say B is a divisor of A if and only if A can be expressed as the product of two integers, particularly B and some other integer, let it be C in this case, right? So we are stepping into the next definition which we frequently discuss, division algorithm. Any integer A can be expressed in the form QB plus R, where we refer B as dividend, Q as quotient and R as remainder. In particular, R should be strictly less than B and it should range between 0 and B, right? In particular, when R equal to 0, then this definition reflects the divisor definition, right? So I can just write A equal to QB, where Q and B are integers, so where both Q and B are divisors of A in this case. So we are least bothered about this case. So when R equal to 0, A by B, even A by Q will result in an integral answer. When we are not aware of this case, when we are not aware of R, then when we divide A by B, the answer may be an integral answer or it may be a real number other than integer. So that's where we are discussing something called greatest integer function, and it will be expressed. So this is the notation for greatest integer function. So more precisely, let me just give an example where A equal to 10 and B equal to 3. So A by B equal to 10 by 3 equal to 3.33333. So it's an irrational number, right? So whereas if I am supposed to identify the greatest integer function of this A by B, so 10 by 3, it's sufficient for me to write only the integral portion and I can terminate the rest of the other decimal numbers. So that's it. So this is the concept of greatest integer function. So there may be a case where A equal to 10 and B equal to 5. So in this case, A by B equal to 10 by 5 equal to 2. The answer itself may be a divisor, an integer. So in this case, they may be equal, but not in all the cases. So that's where we can come to a conclusion that A by B is greater than or equal to A by B. So here we can observe the equality, and here we can observe A by B is strictly greater than the integer function. So this is the preliminaries to understand about greatest integer function. So more precisely, if x equal to 5.25, the greatest integer function of x is simply nothing but 5. Similarly, if y equal to 7.5, the greatest integer function of y equal to simply 7. So that's where we have a property. So x can be expressed as a plus r. and y can be expressed as b plus some s. So this a represents the integral portion phi, and this r represents the rest of the other residues what we have. Similarly, b represents the integral portion 7, whereas this s represents the rest of the residue 0.5. So in this case, when we are supposed to add x plus y initially, normally we will have 5.25 plus 7.5, which will give me as 12.75. Whereas if I am supposed to add the greatest integer functions of x and y, then x plus y will be 5 plus 7, that will be 12. So this is something equivalent to, so I can just apply my associative property. So I can just add these two, later I can just take the integral function, still it remains the same. So the associative property holds good for the greatest integer function. So these are some preliminaries which we are supposed to be aware when dealing with greatest integer functions. So now we are moving into a very important theorem. The greatest integer function of x plus greatest integer function of y is less than or equal to greatest integer function of x plus y, which is strictly less than greatest integer function of x plus greatest integer function of y plus 1. So before going to this example, let me get back again. If x equal to 5.25, x plus 1 equal to 6.25, greatest integer function of x equal to 5, greatest integer function of x plus 1 equal to 6.25, that is equal to 6, greatest integer function of x plus 1, that is equal to 5.25 plus 1, that is equal to 5 plus 1, that is equal to 6. So whenever we deal with greatest integer function, including an integer within the function or excluding or leaving it after the function, the answer doesn't affect. It need not be 1, it can be any integer, a proper integer. So for example, if n is any integer, then the greatest integer function of x plus n and the greatest integer function of x plus n, they both remain the same. In this case, instead of n, we are assuming 1. So I am just adding 1 to the value of x, then I apply the greatest integer function, or I apply the greatest integer function, then I add 1, they both result in the same answer. So if n is any integer, then they both are same, right? So for our convenience, let me take x equal to a plus r, y equal to b plus s, where this r and s lie between 0 and 1. As we discussed already, when they both are equal to 0, the case is obvious. So we'll consider this case, because for this case the case is obvious. So when we shall consider this case. So taking the LHS, the greatest integer function of x equal to a plus r. So the integral portion is a alone. This is the integral portion, so a alone. Similarly, the greatest integer function of y equal to b plus s. So the integral portion is b alone. Therefore, adding these two, the greatest integer function of x plus the greatest integer function of y is equal to a plus b. This is equation number 1. So this is so simple, right? Now what I do is, I just add x and y plus first. So adding x and y, I just get a plus r plus b plus s. Now I take integer function. So integer function of x plus y equal to the integer function of a plus r plus b plus s. So we discussed already, whenever we identify an integer within the greatest integer function, that can be taken outside. Here a and b are integers, so that can be taken outside. So a plus b plus r plus s. So this is our second equation. So when r and s, they both are equal to 0, when this case, when r and s, they both are equal to 0, then obviously 1 and 2 will be equal, so this equality will hold, right? So this both will be 0. If either one of them are non-zero, then we are into this case. If we are into this case, again we have two cases where r plus s may exceed 1 or r plus s may be strictly less than 1, right? So if r plus s is strictly less than 1, so this will be 0 point something, still 0 point something, the integral function will be 0, still the equality may hold. So the equality may hold when r equal to s equal to 0 or r plus s is strictly less than 1. In both the cases, the integer function will be 0, so they both will be equal. If not, then obviously 2 will be greater than 1. I hope you can understand. Let me make it precise yet again. If r equal to s equal to 0, I'll get 0 plus 0. So the integral function of 0 is 0. So obviously 1 and 2 will be equal. If r plus s is strictly less than 1, for instance, if we assume r equal to 0.2 and s equal to 0.3, then that will be 0.5. So whatever is within 0 point something, the integral portion will be 0. Still the equality will hold. If not, then obviously 2 will be greater. So I hope 1 implies 2 is done. Now I am switching over to the third case. In third case, I already have equation number 1. I am adding 1 on both sides of equation number 1. So what do I get? The greatest integer function of x plus greatest integer function of y plus 1. That is equal to a plus b plus 1. So let this be equation number 3. Now comparing 2 and 3. So I have a plus b, I have a plus b. So r plus s and 1. So for this r plus s, I have three cases. In first case, r and s, they are equal to 0. If r and s, they both are equal to 0, the greatest integer function will be 0 plus 0, that is equal to 0. So I write here. So case 1, r equal to s equal to 0. Therefore, greatest integer function of r plus s equal to 0 plus 0 equal to 0. Case 2. So r plus s is less than 1. So if it is less than 1, it will be 0 point something. So if I take greatest integer function, it will be 0 point something. So that will be simply nothing but 0. Third case, if r plus s is greater than 1, it will be 1 point something. So the greatest integer function will be 1 point something. So that will be 1. So these are the three cases. Whatsoever, this will be greater than this particular term, because it cannot exceed 1. So that basis, I can just connect these two. So people may have an equality here as well. So when considering these two, there will be an equality. When considering these two, there may not be an equality as well. So this is the basic condition. So people have to remember this concept. So besides this, there is nothing much left out. So when this belongs to, they both are equal to 0 or they both are less than 1, then obviously they both are equal, and this will be strictly less than. If it is beyond 1, then obviously they will be equal. So that's how this concept is all about. this session, we are about to discuss or to find the highest power of a prime p in n factorial. So if we take any integer n and if we identify its factorial, we are supposed to sort out a particular prime number p probably, and we have to find out the possible factors of that p within this n factorial. So it may sound a bit hard. Let me just get back to the wording, the numbers. So for instance, let me take n equal to 6. So n factorial equal to 6 factorial equal to 1 into 2 into 3 into 4 into 5 into 6. Right? So let me assume p equal to 2. So before assuming p equal to 2 and n equal to 6, this is for our convenience. In general, n may be any positive integer and p may be any positive prime or probably any prime, right? So there may be three cases for fixing that prime p. If p itself is greater than n, if p is greater than n, so since p is a prime number, I can understand that other than p there may not be any other factors which is less than p. So since n is strictly less than p and since p is prime, I can understand that there may not be even a single factor because p is prime, and less than p there may not be even a single factor. So we are ignoring this case. P equal to n. So now we can again from the definition of prime I can understand that itself will be the only factor. So obviously n it will be the single factor for prime p in this case. So we are ignoring this as well. And p is strictly less than n. If p is strictly less than n, then obviously since we are identifying n factorial, p itself, since p is less than n and we are identifying n factorial, the product of all the numbers less than n, p itself will be a single factor. P itself will be a member within that because p is strictly less than p is less than n. N factorial, product of all the numbers less than n. So among that p will be a factor because it is less than n. There may be some multiples of few more multiples of p within that product as well. So that is what we are going to discuss. So when I deal with example, it may be more clear. So that's where I get into a case where n equal to 6 and p equal to 2. So here I can, as I said already, since n equal to 6, I have all the numbers less than n and less than n and their products. So that is the concept of our factorial. Since p is less than n, obviously p should be expressed here, right? So not only p, its multiples also can be observed here, right? So 1 time p, 2 time p, 3 time p is observed there. So what people in general say is p, 2p, 3p, etc., etc., etc. It cannot exceed n. In this case, it is 6. So 3 times of p. If at all, if my n is 7, still it cannot go beyond 6 because 2 does not divide 7. So that's where we have to identify how many factors of p are there. So that's where we are using our greatest integer function p, 2p, 3p, etc., etc., etc. n by p, greatest integer function of n by p times of p. So here 6 by 2, I get 3, exactly 3. So I can stop here. If at all, if it is not 6, if it is 7 for example, then 7 by 2 will be 3.5. So still I should stop with 3 times. So that's where we take the greatest integer function, and that's why we write it as greatest integer function times of p. So this is how we can identify, or in general we can express if n is, this is for we have taken 6 for our convenience and p equal to 2. In general, if n factorial is expressed as 1 into 2 into 3 into etc. into n minus 1 into n, and if we choose some p which is strictly less than n, p will be for sure any one prime within this, and there will be obviously its multiples also. We have to identify total number of multiples. So I can just say p, 2p, 3p, etc. The last should be, of this case, the greatest integer function of n by p times of p. So I hope you can understand this with our earlier example. With respect to that, you can understand this. So this is the total number of total prime factors of p in n factorial. So the highest power of p, obviously it is of the form n by p, because this is greater, this is greater, this is greater, so obviously this should be the largest factor in terms of p. Similarly, we express in terms of p square. So let me go back to the same example. N factorial equal to 6 factorial equal to 1 into 2 into 3 into 4 into 5 into 6. So here p equal to 2. Now if I have p square, so now I have 4. So besides 4, now I may not have additional, because it will go beyond that. 4 square, other than 4 I don't have much. Next 4 will be 8. So 2 times of 4. So 1p square is there, 2p square is not here. So 2p square will be 2 into p square will be 8, which is not here. So that can again be sorted on as n by p square 6 by 4, that is again equal to 1, because I have only 1. There I had 3. For p, if I take p, n by p, then I had 3, 2, 4, 6. If it is p square, I can have only 1. I cannot go beyond that. For example, if I take n equal to 10, if n equal to 10, then 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10, p equal to 2. Now p square, now p square is 4, 1p square, 2p square, 3p square will exceed. So how can I understand? So 10 by p square, greatest integer function. So 10 by 4, so that is 2. Similarly for p cube, similarly for p power 4, so I can just extend this. So that's where, to identify factors of p, there will be n by greatest integer function of n by p, factors of p, n by p square, factors of p square, n by p cube, factors of p cube. So the highest power, so when you are going to identify the highest power, then it will be n by p plus n by p square plus n by p cube plus etc. 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 So this is the basic notation for identifying highest power of p in n factorial. So this is the basic logic to identify the highest power of p in n factorial. So using this concept, we are supposed to discuss a problem. Identify the highest power of 3 in 500 factorial. Maybe in page number 118, exercise problem 7. So that's what we are going to solve. So in this case, n equal to 500, p equal to 3. So the highest power of so we know, first of all, we are supposed to find the greatest integer function of n by p, that is 500 by 3. So that will be nothing but 1, 8 3s are 6, 6 3s are 18, and again 18, and 66. So that is equal to 16. So next I have to go for n by p square, that is 500 by 9, that will be 9 5s are 45, 9 5s are 45, and again 5 5 5 5. So that will be 55. Probably it's 166 rather. So n by p cube, 500 by 27. So 1 time 27, remainder will be 23, 230, and I have solved it as 18 point something. So let me have it as 18. Next will be n by p power 4, it will be 500 by 81, and that will be something like 6 point something. So next will be n by p power 5, that will be 500 by 243, so that will be 2 point something, and p power 6 will exceed 500. So obviously if it is exceeding 500, I will get whenever the denominator is greater than the numerator, obviously the answer will be 0 point something, so we can just ignore them. So now the highest power of 3 in 5 factorial will be n, the greatest integer function of n by p, plus the greatest integer function of n by p square, plus greatest integer function of n by p cube, plus greatest integer function of n by p power 4, plus greatest integer function of n by p power 5. So why do we terminate here? Because when finding the greatest integer function of n by p power 6, 500 by 3 power 6, obviously that is exceeding 500, so obviously I will get 0. So that will be nothing but 166 plus 55 plus 18 plus 6 plus 2. 166 plus 55 plus 18 plus 6 plus 2. So that will be nothing but 247. So 3 power 2 power 47 3 power 2 power 47 divides 500 factorial, whereas 2 power 48 will not divide 500 factorial. So that is the concept. Hope you can understand. So this is the highest possibility in terms of power of 3 that can divide 500 factorial. So obviously 3 power 248 will not divide 500. So let me give a very basic example to understand this logic. Let me go back to the earlier example where n equal to 6. So n factorial equal to 6 factorial equal to 720. 1 into 2 into 3 into 4 into 5 into 6, right? Let me assume p equal to 2 for our convenience. So from here I can just write the greatest integer function of n by p equal to 6 by 2 equal to 3. The greatest integer function of n by p square equal to 6 by 4, that will equal to 1 point something. And obviously the greatest integer function of n by p cube, 6 by 8, so that will be 0. 0 point something, so it will be 0. So now the highest power of 2 in 6 factorial is, so what I get? 3 plus 1 plus 0 is equal to 4, right? So what is 2 power 4? So that is 16, right? So obviously 16 divides 720. if I get 2 power 5, that is 32, you can identify 32 does not divide 720. You can observe, you can calculate and you can observe. So when 2 power 4 divides 720, obviously 2 power 2, 2 power 3, 2 power 1, so that is obvious. So 2 power 4 is the highest power in P or in 2 which divides 6 factorial. So besides this 2 power 4, I cannot find the higher power of 2 dividing the 6 factorial. So in this case, you can just observe. So besides 2 power 4, that is 16. 16 exactly divides 720, whereas 32 does not divide 720. Not only 32, higher power of more besides power 4, 2 power 5, 2 power 6, it cannot divide 720. So this is the logic which we discussed. I hope you can understand. You can just observe, you can just calculate 720. 720 divided by 16 will be an integer answer, whereas 720 will not divide 32. Sorry, 32 will not divide 720. Finally, let me conclude solving one more important problem and I can wind up this session. So if 100 factorial is expressed completely, so for 6 factorial we get 720. Similarly, 100 factorial is evaluated and expressed. Identify the number of zeros at the end. So it is simply nothing but it can be in terms of 10 power something, only then it can end with zeros at last. So what we are supposed to find is highest power of 10 in 100 factorial. More importantly, we have to discuss that, we have to be keen that we have discussed only for prime numbers. So whenever we find an integer other than prime, using our unique factorization theorem, we are supposed to decompose it into prime factors. So now this problem gets reduced into a couple more problems. Highest power of 2 in 100 factorial, highest power of 5 in 100 factorial. Right. So let me just discuss one by one. So n equal to 100, p equal to 2, therefore the greatest integer function of n by p, 100 by 2, that is equal to 50. The greatest integer function of n by p square, that is 100 by 4, that is 25. Greatest integer function of n by p cube, that is 100 by 8, 1, 2. Am I right? Sorry. Yeah, it's right. So greatest integer function of n by p power 4, so 100 by 16, so that will be 5 times 80, 6 times 96, right? 6 times n by p power 5, so 100 by 32, so obviously 3 times n by p power 6, so 100 by 64, obviously it will be 1, n by p power 7, so 100 by 128, that will be 0. Therefore highest power of 2 in 100 factorial is 50 plus 25 plus 12 plus 6 plus 3 plus 1, that will result in 75, 87, 97. You can understand. Let me repeat again. The question is in an indirect format. If 100 factorial is expressed without factorial, or if it is evaluated, identify the total number of zeros at the end. So which is simply nothing but the number of powers in 10. So to identify the highest power of 10, we have to use our decomposition using unit factorization theorem. I am sorting out for 2 first. For 2 I have identified it as 2 power 97 divides 100 factorial. Right. Let me do the same thing for 5. So n equal to 100, p equal to 5. Therefore, n by p equal to 100 by 5, that is 20. N by p square, 100 by 25, that is equal to 4. N by p cube, 100 by 125, that will be 0. Therefore, highest power of 5 in 100 factorial is 20 plus 4 plus 0, that is equal to 24. Therefore, 5 power 24 divides 100 factorial. My question is 10. So I have 97 2's and 24 5's. Only 5 and 2 can fuse to get to give 10. So which means 24 will be the answer, because I have only 24 5's. 5 into 5 into 5 into 5. So out of this 97, only 24 2's will be available to fuse with 5. So obviously minimum of these two, 24 is the answer. So if 100 factorial is expressed or evaluated, the number of zeros at the end, right end, will be 24, because 10 power 24 divides 100 factorial, which means 10 power 25 will not divide 100 factorial. So hence I can come to a conclusion that there will be 24 zeros at the right end when 100 factorial is expressed or evaluated. So that's it, guys. Thank you for your patience listening. Thank you.